let me start by recapitulating what we have done yesterday. So we started discussing the really famous and the most important classical field theory, and that is the Maxwell's theory. And so as every field theory, classical field theory, it consists of two sets of equations. It consists of the field equations, basically given the sources, the current, and the charge density. You can find how the electric and magnetic fields look like by solving these equations. And at the same time, you know that actually if you already solve for these E and B's, then how the test particle moves in this electromagnetic field, and that's provided by the Lorentz force law. So really, you always need these two sets of equations. So now the way I present it is that I said, well, these are fixed, and I'm solving for these, and then these are fixed, and so I'm solving for that. But of course, in practice, if you it's a coupled system, and so you have to solve them simultaneously, unless really you say this is a test particle, and if it's a test particle, it doesn't produce any electric and magnetic fields. So I can just fix these really, and they are not affected by the particle itself. All right. So now what we have done as a second step, so we started with 6 unknowns, E and B, and then we said, well, it's a convenient thing to actually eliminate this E and B in terms of the new potentials, phi and A. So we are trading 6 quantities to 4 quantities here. And the way how you introduce these is over here. And if you plug it into equation 2 and 4, you realize that they are automatically satisfied. So this is really a mathematical convenient tool. And you are using the identities like the divergence of Kel equals to 0. So this is automatically satisfied, and similarly here. But it's actually still you are overdoing it. So still you are actually choosing a description where you have more variables than you really need, and then that are independent variables, and that's reflected by the gauge freedom. So you have still a freedom in your description, and namely, if you do such a transformation where lambda is any function here, it's called gate function, then these things actually leave your field strengths E and B invariant. Okay, so I have this freedom here, and in particular, you can use this freedom to choose some very nice gauge, and the gauge I'm using here is the Lorentz gauge, which is written here. But of course, you can use other gauges as well. And various gauges are good for various things. So depending on the kind of problem you want to solve, you may impose other gauges as well. But this gauge actually allows me to rewrite the remaining 2 source equations, Maxwell equations with sources 1 and 3, as a wave equation. So you have this box operator acting on phi or A, and then you have the sources on the right-hand side. And so you see that these equations are exactly the same. So really, if I write it in Cartesian coordinates, you get a same wave equation here and the same wave equation for 3 components of the vector potential A. And so if I solve one equation, I solve the other as well. So now we are trying to really find the solution of these equations. And they are given because they are linear equations. They are given by the solution of the homogeneous equation. So with the right-hand side equal to 0. That's okay. Quite complicated to find sometimes. But then the general solution is this solution of homogeneous equation plus the special solution, which is any solution that solves this equation with that given right-hand side. And you'll be finding the solution by a method of Green's functions. So just to stress, of course, now I'm finding the solution of these equations, but still, once I find it, I have to make sure that it satisfies my Lorentz gauge. So I really have that condition there still to be considered and to be satisfied, and so that will provide some additional constraint on your solutions. All right. So now, what is the method of Green's functions? So basically, the idea is let's find a miraculous G, and once we have that miraculous G, we can write down this phi special. So phi special by simply integrating this G, which now depends on R prime, T, and T prime over the density over the right-hand side of your equation. And so to see that, you simply imply a box on both sides. And you see that this is your definition of your function G. And if you use the definition, then it will give you the equation you want. So now why I can write it in this way is because you have isotropy and then you have time translation symmetry. And so that's why it can only depend on the difference of these things. All right, so now we have started solving this equation here, and that gives us our miraculous G, which we need here. And we did it by going to the Fourier space. So we just Fourier transform everything. We Fourier transform R and T, going to the K space and the frequency space. And so by using that equation over there, we found that this G K omega is simply given by 1 over K square minus omega square. So now what we have to do is really to do this. So plug it here, plug it back here, and do the integral to see what happens. All right, and so the trick is to use the spherical coordinates in the K space. So I'll be really, so K is some vector in this K space. I'll be choosing such coordinates that basically the vector is pointing in the radial direction. So this thing will just become a magnitude of K squared, so the radial direction K. And then I have a scalar product of K with respect to R, which is some fixed vector here. And so this will be just the magnitude K, magnitude R times the corresponding angle in between them, cosine theta. Okay, so this is equal to 1 over. Are there any questions before we go into this? Any questions to this, what I said? Okay, so it's 1 over 2 pi to the power 4, and then going to spherical coordinates. So that means I'll be integrating over phi angle and over theta angle and over K, which is the magnitude. So of course, nothing depends here on phi. So the integration over phi simply gives you 2 pi. And then the measure is K square dk and the cosine theta. So that's the measure for your spherical coordinates. And then you have the exponential. And as I said, you're taking that this is the magnitude K and then the magnitude R and then cosine theta. And that's minus I omega t. And then you have your Green's function here. Well, this is just a magnitude, so it's divided by 1 over K square minus omega square, so just a magnitude. And then you integrate this over omega as well. The omega as well, and I hope I didn't forget anything. So this 2 pi simply comes from the integration over the phi angle. Okay, so now if I integrate the cosine theta, I integrate from -1 to 1 or something like that. And so what it means is that basically in the integration over the cosine theta just gives me +1 or -1 over here. Okay, so this is equal to now the 2 pi. It's 1 over 2 pi to the power 3. And then I still keep the integration over dk and the integration over the omega. But then I'm plugging for cosine theta either +1 or -1. So it will be e to I kr if I use +1. And then minus e to minus I kr. And then k square minus omega square. And then I have this e minus omega t. Okay, but that would be too simple. So what I also have to do is when I integrate this, I have to do 1 over IKR. So it'll be IR and then k, and then this thing here, IRK. All right, so now I see that one of the k's actually cancel. So this comes from the integration of the exponential. So this k cancels this k, so let's put this k here. And let me rewrite this as 1 over 2 pi cube integral, and let's say an integral over the omega e to minus I omega t. Sorry, that's the capital T. So many mistakes. And we have also 1 over IR. And then let me call the integral over k simply an integral I. And so what this integral I is this e to I chi. So it's an integral over dk, and then k, and then e to I kr minus e to minus I kr divided by k squared minus omega squared. Everybody happy so far? Did I do any more mistakes? Did you find any more mistakes? Right, so we have two integrals left over the magnitude of k and over omega. So now the integral over k is of course from 0 to infinity. It's like a radial thing, so I'm integrating from 0 to infinity here. And then you can observe that this term is exactly the same as that term, provided that I extend my integration from minus infinity to infinity. So then I have just the first term, and then the second term is automatically included. So what we have to do is to calculate I, which is an integral from minus infinity to infinity, and there will be some function fk dk, where this function is k times e to I kr k squared minus omega squared. Everybody happy with this? So simply grouping the two terms together by extending this integration to minus infinity. So of course this is a complex integral and has problems because you are integrating on the real line from minus infinity to infinity. However, that's precisely where you have your poles, right? So then, if you draw this in the complex plane, so this is your k real, but you have one pole at k equal to plus omega, and another pole at k equal to minus omega. And so then you want to go really and calculate the integral from here to there, and you cannot actually cross the poles. So you have to decide how to avoid the poles. So now the way I will avoid the poles is I simply just go around them. My choice is to go above the poles. So I do the integration, which goes like this. And then, of course, the trick is to use the Cauchy's theorem or whatever. So you have to close the integration contour. So you go and close the integration contour. So you integrate over this thing here, going like that, going like that. Okay. So now what you want is that this circle is at infinity. And now, of course, so now we enclose, so whatever is inside, you would be calculating how many residue are there, but there's nothing inside, so actually the total integral is 0, right? Now what you can show that there are some important lemmas or whatever, something like Jordan's lemma, that the integral over this thing, over this function, actually, the function is nice, and so the integral at infinity is actually 0. So there's this thing, integration over this thing goes to 0. And so then if this thing is 0, then if I have an integral I1 here going around that one pole, and then integral I2 going around the other pole, then that's the sum of these integrals is precisely equal to the integration over my real line. Okay. Who has done complex analysis and it's very trivial for the person? Is this trivial for everybody? If not, just open any complex analysis textbook. So anyway, so the statement is that the integral over the real line is precisely equal to the sum of these integrals I1 and I2. So I is equal to I1 plus I2. And so basically going around these poles, that's all you have to do and to calculate this integral. And so another statement is that if you actually go around the pole, it depends how, what angle I'm actually sweeping. Here I'm sweeping just half of the circle. So the angle is actually pi. So then this is equal to I pi, and then the residuum of that function f. And so one residuum is at the pole minus omega, and then I have the other residuum at omega. Okay, so now residuum is basically what happens, at this pole. So if you just naively plug k equal to omega, of course your function diverges. And so the trick how to calculate this residua is basically, so the situation is quite simple because you have single poles in k plus omega and k minus omega. So for example, if you had 1 over k square, you would have double pole at 0. But now this is really simple. I have k minus omega times k plus omega, so it's really single pole. And the prescription to calculate the residuum is to multiply by k minus omega and take the limit k goes to omega. Okay, so if I want a residuum at, let's say, plus omega, so I write this as k minus omega and then k plus omega. I want the residuum at k plus omega, so this is the problematic term. So I multiply the whole thing by k minus omega, which kills this term here, and then I simply evaluate whatever remains at k plus omega. So then it's, okay, so that's this thing here. So I'm plugging k equal to omega, and then e omega r. And then if I multiply by k minus omega, then I have just 2 omega here. And similarly here, and you'll find the same result. So this is e. So this is omega e to minus I omega r, and then 2 omega. So in other words, this integral is very simple, and it gives you I pi over 2 e minus I omega r plus e plus I omega r. Anybody is not happy with this calculation? Everybody's happy. Who is not happy? Raise your hand. Everybody is happy, so it's trivial. Okay, that's a proof. So we have this integral. We calculated I. So now let's plug it back for our g. So our g is 1 over 2 pi cubed, and that integral from minus infinity to infinity e omega, and then we have this 1 over IR here as well. And then we are plugging for our I. So it'll be I pi over 2. And then I can group the terms together. There's always an exponential which is in omega and I. So I will have a term which is e to minus I omega, and then I will have t plus r. And then I'll have term where it's minus r. So e to minus I omega t minus r. And so this is what it is. Right? I'm just grouping the term is this minus I omega t. Okay, very good. So, well, so I cancel. And then some pi's also cancel. So we have 2 to 3 is 8. So it's 1 over 16. Why is it 1 over 16? Did I drop something? 2 to 3. Yeah, that's fine. So this is 1 over 16 pi square. 1 over 16 pi square, canceling this pi here and this 2 here and this thing here. And that is still r. So let's cancel this r here as well. Okay. So now if you look at this thing here, you are integrating over omega, and you're integrating exponential, and the second term is exactly the same, but whatever the argument here is slightly different of the exponential. So now this is nothing else than just a definition of the delta function, right? In this exponent t minus r, or in the exponent of t plus r. So it's just a one-dimensional delta function in this case. So we have that g. Okay, so g is, okay, a little stupid, 1 over 8 pi r, and then I'll put 1 over 2 pi, and then the exponentials, the omega, and then e minus I omega t plus r plus minus plus e minus I omega t minus r. So this is what it is. So now this is just a delta function. And so this thing will give me a delta function of t plus r. And this thing will give me a delta function of t minus r. So this is a beautiful result. So we have 1 over 8 pi r, and then delta t plus r plus delta t minus r. So now you have two parts, and these two parts can be combined together, but they mean different things, right? So this thing here is something you would expect. So this thing sort of describes a propagation with the speed of light on the line cone to the future, right? So I have some source here, and this source sends a signal. That signal propagates at the speed of light, and at later time I observe it here. Okay, that's precisely what this term describes. However, this thing here is the advanced signal. It means I have the source here, but actually the observer would see this source earlier in time, because the thing actually propagates the other way around. So this is the advanced potential, and this is the retarded one. And you see that your mathematics is giving you both of these things. By the way, you can also combine the things together by using this beautiful identity Dan showed you, that you have delta of f of x. It's something like delta of x divided by f prime x, right? So you can combine this to be 1 over 4 pi delta r square minus t square, which is really showing you that this propagates on the light cone. So there's missing c square here, but really I have to have r equals to t, which is the light cone propagation. Okay. So now, of course, we are used to these things in the nature, right? So you have a signal, and then it takes some time before that signal reaches the observer, right? So this is what we are used to. And this is something really, really strange, which we never observed. And so does it violate the causality or stuff like that? So this is problematic. And so what typically physicists do is that they simply say, well, I observe this thing here. I've never seen this, so I just kill it. Okay, and so typically, or standardly, they simply throw away the advance potential and keep only the retarded one. Because that's not what we observe in physics. So you are basically throwing away half of the physics. Away 1/2 of physics. So basically the argument is, the mathematicians can do whatever they want, but we don't care, right? This needs to be in correspondence with what we see. And so that's why we have to kill these things. Okay? And so if you do so, then your Green's function is just given by this delta function here, delta t minus r. And then if you want to find the corresponding phi, well, we just use this delta function t minus r. But of course, the calculation was valid, so this is a horrible thing, right? So the calculation was valid provided that we had both advanced and retarded potentials. So you have to have some of both these things. So now if you throw away the retarded one, the advanced one, you have only half of the solutions. So what people do is to get the right mass is that multiply by 2. So they only use the retarded thing, but they multiply it by 2. Okay, so multiply, so take 2 times the retarded one. Okay, and so our Green's function, well, is simply 1 over 4 pi r delta t minus r. Okay, so and if you use this retarded Green function and you plug it for your solution, you find that phi special is simply given. So now you have 4 pi there in front of rho, and so that cancels those 4 pi. And so this is simply an integral. So now you can do the integral over time, prime, right? So remember, capital T is t minus t prime. So I can do one integration and use this delta function here. Basically, instead of t prime, I'll be plugging t minus r. Just a second. So the result is I killed the integration over time. So I have to evaluate rho at t prime, which is now t minus this r, and then r, and then what stands here is, okay, so r is r minus r prime, the magnitude now, so it's t minus r and divided by r. And that's your solution that's your special solution for your phi, given the sources we have here. And it's, okay. What was the question?
Yeah, so in order for this delta function to contribute, its arguments are t, which is the time interval, and r. R is by definition positive since it's a
magnitude
vector. Okay, but t also has to be positive because earlier we used the positiveness of t in order to close the contour of the integral in the upper complex plane. This guy just is 0. It's not something we set to 0.
I'm saying that I'm cheating here.
No, we used the positiveness of r, right?
R is positive, so the only...
So R has to be positive, I agree with that statement. You are saying capital T has to be positive as well,
yeah,
because that integral wouldn't converge, you are saying. I see. So maybe there is some theta t function as well.
Yeah, there is. That's.
I see. So okay. Thank you. So.
But then we have to justify the ×2 factor, just like this.
Yeah. Okay. So maybe not everything I'm saying here is right. Can you make it right?
What?
Can you make it right?
Yes, just set the guy to 0 and that's it.
Yeah. But then you need the factor of 2.
Yeah.
Okay.
I think there is a missing factor of 2 somewhere in the calculation. I don't know where at this point, but there should be a factor of 2.
Can you say again what
Oh, sorry?
Can you say again what big T?
No, because it's not. It doesn't figure in the integral here. It's not. So you don't need to.
So basically, what
You just need to.
Mattia is saying that
Oh, I did it differently.
the important part of the calculation was disclosing the contour here.
Yeah, but
And he's saying this contour will actually go to 0. The integration over this contour will only go.
This is okay.
Huh?
Because I mean, our integral here, like with
Yeah.
just the k part, doesn't have the t anyway. So
we only need the big R to be positive,
Yeah.
which it is, so
Yeah.
it's fine.
So it's okay.
yeah.
Yeah, no, I did the integral differently. Maybe we'll compare later, so not too much.
Okay. So anyway, so this is a very important formula, and of course you have the same formula for A, right? So this is your solution for phi, and we will use the same thing for gravity when we discuss in relativity course. You will see that you have precisely some kind of wave equations there as well, and then you'll just use the result that's really the phi is given by these retarded potentials. So there you will have the perturbations of the metric will be given by the retarded potentials. And so for gravity is the same thing, but now you replace phi with g mu nu, and this will be your source t mu nu. Okay, but I will not go through this calculation again.
Why did you use pi I when you did the residues instead of pi?
Because you are
Is it
like
because
how you go around the pole, and there's some like mathematical theorems, and so how much angle you sweep, that much pi you put there. So if you go around the whole thing, it's 2 pi I. If you just go half, it's pi I.
I wondered if that's a thing?
Fractional residue for simple
Fractional residue? Okay.
Yeah, so there is some mathematical theorem behind. So maybe I'll just try to find these theorems and I'll put them in the study text so that you are all happy with this. All right, so now I'm doing not so good in time. So I'll skip whatever the radiation reaction force and whatever the Feynman story is. And let's see if we have 5 minutes at the end of this lecture to return back to this. Because it's real fun, but in order to be ready for today's tutorial, I need to go to the relativistic description of these things. All right, so part C from Maxwell to relativity. And so let me just briefly mention what symmetries you have. What symmetries of Maxwell equations. And so this is a really beautiful theory which has all the symmetries you want. So first of all, of Maxwell's theory, of symmetries of Maxwell's theory, maybe better, of Maxwell's theory. So first of all, it is a gauge theory. Gauge theory, which is really nice because we know that all modern theories are gauge theories, precisely related to the fact that you are using description with some constraints, with some gauge freedom. Second, it is actually invariant under Poincare transformations, which means under Lorentz plus space-time translations And in other words, what this means is that the theory is actually relativistic. So special relativistic. And we will concentrate on this point here. It has also a conformal symmetry. It's a conformal field theory. So in particular, it's invariant under change of scale. And finally, if you have the source is equal to 0, you have also interesting duality, which is the electromagnetic duality. Basically, you can change E to B and B to minus E, and the equations remain the same. So all these symmetries are hiding in the Maxwell's theory. And so that's why it's like really a prototype of everything you know about modern physics at this point. Okay, so what I'll do is that I will concentrate on this invariance under the Lorentz transformations, and then we can add translations a little bit later. And I'll be doing something which is probably obvious to everybody here, but I just have to do it so that we have this notation of which we'll use later. Okay, so the first step to realize that actually the Maxwell's theory is invariant under these transformations or is relativistic is that we know that the Maxwell's truth predicted the speed of light. Okay, so we predicted that we have these waves, and these waves propagate at an absolute speed, c. We said that c equal to 1 in our units, but it doesn't matter. What matters is the very existence of this speed. But what it means is that now I can convert time to a distance, right? I can always take time and multiply it by c, and I get something which has units of length. That means that I can unify time with space. Okay, the existence of c of c, which in our case is equal to 1, and so I'll not really write it later on, means that we can convert time, to length, and we can introduce the space-time. Space-time. So, in other words, now I'll introduce the coordinates x mu, which will be ct and then xi. So these are my spatial coordinates. Now I include the time coordinate as well. And of course, this was done by Minkowski. And at first, Einstein hated it, right? So he said, well, so he had these, beautiful papers about how E equals to mc squared and stuff like that, and Lorentz contractions and whatever. But then Minkowski came and said, well, I can describe everything provided that I introduce this Minkowski metric where time has like special minus, and then I have the other pluses, and then Einstein hated it, right? So he said, well, you are just obscuring my nice physical results with this horrible math which nobody understands. But of course, later on, he realized that's precisely the way to go, and he wouldn't have discovered general relativity if Minkowski didn't come with this concept of Minkowski spacetime. All right. So that's first note. Second remark is that notice that we use these indices mu, the Greek indices, and they run from 0 to 3. So these would be the spatial things, and the Roman indices, they just denote the spatial part. So these are the spacetime indices, and these are the spatial indices. So now, as Neil claims, this is an absolute proof of the fact that Greeks were more clever than Romans, right? So Greeks already knew about the space-time, whereas Romans only knew about 1, 2, 3, right? So that's the proof. But if you think about it, it's probably true because just Romans were like just huge military power and they didn't really care about science too much and whatever. But Greeks were like really creating nice things, right? So okay, so we have this. Let me just write it. Greeks. More clever than Romans. Okay. So we have this. We have the space-time coordinates. Of course, we can now do the same thing with the derivatives. So I'll be introducing the notation d mu, which is d over dx mu. But now this is 1 over, this d over dt and d over dxi. And at this point, just it falls from heaven. But you can introduce other symbols which are eta mu nu. And they are simply matrices with one minus sign and with the other plus signs. All right, so now I can introduce the matrices. And then you write eta, alpha, beta, is minus 1, 1, 1, 1, and 0 everywhere else. So it's only on the diagonal they are non-trivial. And then you can introduce its inverse. So eta, alpha, beta, it looks precisely the same thing. 1, 1, 1, 0 here. And these are inverse matrices, meaning that if I sum over the index, eta, beta, gamma, I just have to have delta, just unit matrix, delta, gamma, alpha. Of course, I can sum over the other index as well. I can sum over the first index here, over any indices. It will be true. Okay. So we have these matrices, and we will use these matrices to rise or lower indices. So can use these, to rise or lower indices. So we will see that we will have later on some objects which have index either up or down. Well, we already see that in coordinates, so the coordinates have index up. That's actually misfortunate because that's not really what you want to do, but the other one is correct. So the other object is a covector. There's an index down. The x mu looks like a vector. Well, it is a vector in special relativity, but it won't be a vector in general relativity. So x mu are simply coordinates, and it's better to think about them like being just coordinates. But in special relativity, they also happen to be a vector. Anyway, so now once I have the vector, I can define the corresponding covector by simply lowering the index. So I start with a vector v nu, and then I can lower the index using the eta mu nu. And similarly, I can use the other one. So if I have a covector, I can rise the index. So I have covector omega, and I can rise the index to get this thing here. So the index which appears only once on each side is the important index. So in our case, the index mu is the important index. But the index nu appears twice. And what it means is we are using the Einstein summation convention, which is summing over nu equal to 0, 1, 2, 3. Right? So this is just a sum, eta mu nu v nu, where nu goes from 0, 1, 2, 3. And so just to stress that, we call this index a dummy index. It means we are just summing over that index, and that index doesn't mean anything. in other words, I can just rename that index to anything else. I don't have to use new. I can just use alpha or beta or whatever, and it'll still mean the same thing. So the index is dummy. It doesn't mean anything. Okay. So because of this nice form of these eta matrices, basically the indices with indices down and up are the same apart from the time direction, apart from the 0 direction. And you are just picking up the minus sign. So if v mu is just v0, vi, then v mu in special relativity is just minus v0, vi. So the only thing which you are getting is this minus sign here. Okay. So now notice also that our box operator, which was minus d square over dt square plus d square over dxi square, summing over all I can just write simply using this matrix here as eta alpha beta d alpha d beta. Or I can raise this index and lower that index. So it's the same thing as eta alpha d alpha d beta. Doesn't matter. Okay. Any questions so far? Is anybody here who hasn't seen this? Okay, that's perfect. So it's very trivial. So now what we want to do is that we want to rewrite the Maxwell equations in the form, in the special relativistic form, where it will be obvious that these are really invariant with respect to the Lorentz transformations. So in other words, this will be true if we can write the objects in terms of these vectors, in terms of the indices, Greek indices, nu and mu and whatever. Okay. So we start with the potential. So Maxwell's theory in relativistic notation. So we want to write everything in terms of the object which have the right Greek indices. And so the best way to start with is with the potentials. So you have 4 potentials, phi and a. A is already a vector. So if I combine them, to something which has 4 index, a mu, there's only unique way how to do it. So you introduce a 4 potential a mu, which will be simply combine these things together, and this is your 4 potential. Now you may be interested in writing the Lorentz gauge condition. So then Lorentz gauge condition, and you see it's simply a derivative of these things, and you sum over I here, and you sum over t, but this is precisely at. So it's not surprised that you can write it in the way d mu a mu equals to 0. Okay, so that's our gauge condition. Now you're interested in what are our gauge transformations. So you see that the gauge transformation for the phi thing, it only goes with the time derivative, and the spatial thing goes with the spatial derivative. So the gauge transformation is simply going from a mu to a mu plus d mu of lambda. And you can check that it precisely translates to this thing here. So that's our gauge transformations. Finally, if you introduce also a forcurrent, so now I want to combine, so you see, It's obvious, right? So I have combined phi and A to A mu. So it's obvious that I have to combine rho and J to J mu. So for current, J mu is just rho and J. And then if I do it, this equation is just box on A mu. Box on A mu equals to minus 4 pi J mu. And that's my wave equation in this Lorentz gauge condition. So now we also derived the solution of the special solution of this wave equation. And the special solution was that A mu special is given by this retarded thing. So D3 R prime. And now we had rho because we only studied phi. But if you include A as well, then you would have J. But they are now combined to J mu. So it's just J mu T minus R prime divided by R minus R prime. Okay, and so that's your solution, the special solution of your wave equations in terms of the 4 language. Okay, so far we are just rewriting whatever we had in terms of these indices. So now why this is really invariant with respect to the Lorentz transformations. So we have to introduce what the Lorentz transformations are. Okay, so let us consider a linear transformation. Why linear? Because only linear transformations are non-singular. Right? If you have any other transformation, it's very likely that at some point there will be some singularity. You will just encounter some problems. So that's why linear transformations are nice transformations. And so I'm going from the coordinate x mu to x mu prime equals to, now lambda mu nu is just a constant matrix, and then x nu. If it's linear, it's also invertible, unless this matrix is degenerate. So I want this matrix, so it's a linear transformation, but I also want this matrix to be non-degenerate. And if it's non-degenerate, I can find its inverse. So I can also revert this as going from x prime mu to x mu, which will be the inverse of this matrix, lambda mu nu x nu prime. Okay, so now this is whatever the transformation I had. This is my new transformation, which is the inverse transformation. So lambda mu nu, lambda tilde nu beta is delta mu beta. Okay, that's just a definition of the inverse transformation. And again, you can also sum over the other two indices. So if I have mu here and beta here, and I would have alpha and alpha, this must still be true. Because there's only one inverse for a matrix. Doesn't matter which index I contract. If you have a minus 1 is equal to 1, it's also a minus 1, a equals to 1 for matrices. If you have operators, that's not true. Okay. So now it will become complicated. All right. So now what you want to do is that you basically want to rewrite these Maxwell equations so that they preserve their form if you change these transformations, if you do this transformation. So let's ask, how various quantities change under these transformations, and let me start with a transformation of a derivative, and so for that we have the chain rule. Okay, so now we're interested in how an operator dx prime mu looks like, and I use the chain rule, so this will be given by the old coordinates dx nu dx prime mu d over dx nu. So now you look at those definitions. So what we need to find is how dx nu over dx mu prime looks like. Okay, and you see, well, I have different indices, but it's the second line I have to be using. So you see that it transforms according to lambda tilde. Okay, so this thing will be lambda tilde nu mu d over dx nu, or yeah, this is what it is. Transform it according to lambda tilde. So second, I have my Lorentz gauge condition, d mu a mu equals to 0. And I want this to look like the same in the prime coordinates. So what you require is the same form of the equations. And so what I require is that d mu a mu equals to 0 must be the same thing as d mu prime a mu prime. This is what you require. But you know how d mu prime, so this is d mu prime. So you know how that transforms. So d mu prime is just lambda tilde nu mu d nu. And so this gives you how the a mu has to transform, right, in order this to be true. And the statement is that if a mu prime transforms as lambda mu nu a nu, then if I use for d mu prime this thing here, so there will be lambda tilde, and then plug instead of a mu prime the lambda, you will have lambda times lambda tilde, but they are inverse. So they will give you 1, and they will give you precisely what you want, that it's equal to d mu a mu. Okay, so now you have how this thing actually has to transform. So now we know how the derivatives transform, and we know how the vector potential transforms. And we just make a generalization. So let's call any object that transforms as the derivative to be a covector. So a covector, or a form, one form, is an object which has index down and transforms as a derivative. So it's given by lambda tilde nu mu omega nu. So S derivative. That's your definition. You call an object a covector or a one form if it transforms this way. And you call an object a vector if it transforms like the potential does. So A mu V mu prime is lambda mu nu V nu. And so as potential. Okay, so this is your definition. And you see that these objects actually transform sort of inversely, right? So the matrix lambda tilde is inverse to lambda. And so these objects transform differently. They live in a different space, as we shall see soon in general relativity. And they are, because they are different objects, they transform differently. So now if you have an object which doesn't transform at all, you call it a scalar. So S. And so if you have S x mu, the same thing as x mu prime, then you call it a scalar. And then you have also tensors. It's simply an object which can have lots of indices, but each of the indices transforms either as a covector or as a vector. So example, e.g. T mu nu alpha, then T mu nu alpha prime will be, so this object, this index transforms as vector, so you'll have lambda mu mu hat, and this vector, this transforms as a vector, so lambda nu nu hat, and this thing transforms as a covector, so lambda tilde alpha hat, and then you have T mu hat, nu hat, alpha hat. Okay, so this is the original object, and this is the object which transforms later. So now you just transform each and every index this way. Oh no. Questions so far? Time. So now we know what vectors and tensors are. So now, is there any restriction on these linear transformations, lambda? And the statement is, yes, we want our box operator to look like in prime and non-prime coordinates the same way, right? So we want that our box operator takes the same form, preserves form. That's the physical requirement. I want the box operator to look like the same way in the prime coordinate and in the non-prime coordinates. So in the non-prime coordinates, I have this is equal to eta alpha beta, for example, d alpha d beta. Now, in the prime coordinates, it should be eta alpha beta prime, d alpha prime, d beta prime. So this is the derivative in the old coordinates. This is the derivative in the new coordinates. But what I really want is, so this thing is just minus partial over t squared plus d over dxi. So now I want that this is the same form. So it must be also minus d squared over dt prime square plus d over dx prime I square. Okay, so in other words, this thing actually does not change, because otherwise I would change the form of this thing. So this is equal to eta alpha beta d alpha prime d beta prime. But I know how these alpha primes, how the partial derivatives is index up transform. So this is eta alpha beta, and then they transform according to the standard lambda transformation. So it's lambda alpha gamma lambda beta delta d gamma d delta. Okay, that was really stupid. Okay, so now this is a perfect opportunity to rename the dummy indices. Anyway, so what you require that this thing here to be the same as this thing here, right? So this will be only true if this thing is eta gamma delta. Okay, and then I can rename gamma to alpha and delta to beta, and then they'll be the same thing. Yeah, just dummy indices. I'm summing both. So you require that this is true. And this is precisely the definition of Lorentz transformation, right? So what you require is that basically, if you write it in terms of the matrices, so anyway, so you have lambda, eta, lambda equals to eta, right? And that's a definition of the Lorentz transformation. So now, in order the box to remain the same, I have to further specify my linear transformations, and they have to satisfy this relation. And the statement is, anything that satisfies this relation is called Lorentz transformation. So now, by the way, if you take the determinant of this, so you have, very schematically, you have something like lambda t eta lambda equals to eta. If you take the determinant of these things, well, determinant of eta is -1. And then you know that the determinant of the product of the matrices is just simply the product of determinants. So from here you are learning that, and then also you know that determinant of lambda t of the transpose matrix is the same as the determinant of the matrix. So what you are learning from here is determinant of lambda square equals to 1. So determinant of lambda. So determinant of lambda is either +1 or -1. So if it's -1, the transformation is not simply connected to your identity matrix, right? And so that's called improper Lorentz transformation. An example would be, I think, parity or something like that. But if determinant of lambda equals to 1, then you can actually connect continuously to the identity matrix, and this is called proper Lorentz transformation. Questions, comments? Yeah.
How could you reason that? I mean, eta alpha beta prime is eta alpha beta. Can you please?
Oh, because I just really, so this is precisely that I want to preserve the form. So in the new coordinates, I just so in the old coordinates, it looked like dt square plus d over dxi square. Okay.
Yes.
So now in the new coordinates, I want to have precisely the same form. I want to have minus d square over dt prime square plus d square over dxi prime square.
But what didn't you use it in the last line when you defined the Lorentz transformation? Because you explicitly wanted this eta lambda lambda as eta gamma delta. That is where you wanted.
No, I just derived this, right? I don't know. So I require that this is true, that in the prime coordinates, the eta basically doesn't change, right? You can do it many ways, right? You can do it many ways. The important thing is, as long as you get the right Lorentz transformations, it's fine.
I think you're already using the definition that the metric tensor is invariant under the Lorentz transformation. So that
No, I'm saying the equation will only preserve the form if it's invariant under the Lorentz transformation, right? So that's precisely this, right? So I derived that it has to be invariant under the Lorentz transformation because I want to preserve the form of the. Yeah. But yeah, it doesn't matter how you derive it, right? So as long as this is true statement, then it's fine. Okay, so we have 5 minutes for the Maxwell tensor. Not enough, but anyway. So we already know how the potentials actually look like in this for relativistic notation. Now you want to know how the vectors E and B look like in terms of the four vector notation. And I know that you had a tutorial with Tibra on showing that actually you have to combine them to a rank 2 tensor, where you really show how the things properly transform and so on. But it's basically the result is obvious. So why is it obvious? Is because of this thing here. So you know that E and B are derivatives of the vector potential, right? So let's say Maxwell 3. Field strength, right? So we start with the potential A mu, right? And then you see that you have to apply some kind of derivative on this A mu to get a new object. So this could be a first proposal. You take d nu A mu, And the question is, does it describe A and B? Okay. Does it describe E and B? And you immediately see that this almost works, but not quite. You know that these are 6 quantities. There's 3 quantities E, 3 quantities B. However, here you have 4 derivatives, and then you have 4 indices here, so you have 16 quantities. Right? So this is not good. This is 16 components, too much. 16, too much. However, you can decompose this into something which is symmetric and which is antisymmetric. So now I decompose this into the symmetric part. So d nu a mu. So now I symmetrize. Well, and the antisymmetric part, which is d nu a mu. So this is the antisymmetrization. So I'll use this bracket here for antisymmetrization, and this normal bracket for symmetrization. So this is the symmetric part, and this is the antisymmetric part. So then the question is, how many components do you have if you just take symmetric matrix? You have 10. Okay, so this guy has 10 components. And how many components do you have here? 6. Okay, so now it's obvious. Right? So we know it has to be a derivative, and we know it has to have 6 components. With nothing else you can write down, right? So you define f mu nu to be d mu a nu minus d nu a mu, which is the antisymmetric thing. By the way, the antisymmetrization is this factor. So this is 2 times d mu a nu. So if I put this bracket here, it's 1/2 of the antisymmetrization. Okay? And this is what it has to be, because there is nothing else with 6 components I can form out of this derivative here. And then if you do it, then you find that this is minus ex minus ey minus ez. And then you have 0, it's antisymmetric on the diagonal. So, and then you have bz, and then minus by, and then bx, and then the antisymmetric thing. So that will be plus ex plus ey and whatever. And you can explicitly check that, really, if I write this down here, I am recovering these expressions here. Right? So now we basically combine together E's and B's, and they are contained in this antisymmetric matrix F mu nu. And that matrix is called Maxwell field strength.
Well, I have one question. Those are the components of the vector, right? Not the covector of E and B. Because sometimes I get confused when you can put like B, the second component of the covector, not the vector.
Well, so here you are using just the Euclidean notation, so it doesn't really matter. Yeah.
No, because if you have the other metric, like the plus 1 minus minus minus, there it changes, right?
Okay, so are you asking this? So then you can define this object with this indices up. I'm rising then using this eta, but you know, so here these are time and x components, but the spatial components actually don't pick up any sign. So it's only the time components. So then all I do is that I just change signs here. So it would be plus ex and plus ey and so on, plus ez. And I don't do anything with the spatial components. Bz minus by bx. So now it's easy to check that this thing here is invariant under Lorentz transformations, right? So remember, the Lorentz transformation is just going from a nu to a nu plus d nu lambda. So if I change it here, all I'm doing is I'm taking d mu lambda, that's the term I'm adding, but then I'm subtracting minus d mu lambda. And so this will leave the field strength F mu nu invariant. Okay, so this thing leaves F mu nu invariant as it should. Okay, so now let me just write down the full Maxwell theory, and I'll return to it tomorrow. So once you have F mu nu, you can write down all the Maxwell equations, and they actually have very, very simple form. And you can also write down the Lorentz force law. And because you will use it in today's tutorial, let me just write it down without any explanations, and then we will derive it tomorrow. So the statement is that the equations 2 and 4 are equivalent, so they don't have any sources, so they must be just given by some operations with F mu nu. And that operation is you just take a derivative F mu nu lambda, and then you antisymmetrize everything. So this is 1/3 factorial F mu nu lambda minus F nu mu lambda plus 4 other terms. And this is equal to 0. So that's the first set of Maxwell equations. So I'm just doing all the possible permutations of the indices, and I pick up the minus sign if it's an odd permutation and plus sign if it's an even permutation. But you can also write it in an equivalent way where people put cyclic, and that's you just take even permutations. So this is just F mu nu lambda plus F lambda mu nu plus F nu lambda mu, and you can show that this is also true. And the equivalence between the two things is simply from the fact that F mu nu is antisymmetric in the index mu nu. And you can show that always two terms in the first expression combine to two terms out of the equation. So that's equations 2 and 4. Then you have equations 1 and 3, and they are even more beautiful. So you see that you have to act with some differential operator on my E and B. So act this differential operator on my F mu nu, and you have to get a source. And the right thing to do is this thing, minus 4 pi G nu, and that's the other set of Maxwell equations. So one set is this thing, F mu nu cyclic equals to 0, or F mu nu lambda completely antisymmetrized is equal to 0. The other set is this thing. And finally, if you want the Lorentz force, well, what it could be, right? So it's only one way to, so dp, so I have to generalize p, the momentum, to the 4 momentum. So I just put it in index mu. Okay. So dp mu, now time is not the right scalar thing, it's actually just one of the coordinates, so that's not a good thing. But you can introduce sort of an invariant time, proper time, tau. So that's the left-hand side. So E is E, of course. You cannot change anything about that. And then you see that this thing here combines E and B. E and B are combined in F mu nu, right? So the right-hand side is linear in E and B. So the only thing which is linear E and B is F mu nu. I just have nothing else. And then you see that what enters here is also the velocity of the particle, right? So now I have to combine the velocity to something which index with the Greek index, and that will be the 4 velocity, right? And that's it. Okay, so that's the derivation of the Lorentz force law in the relativistic notation. And this is your complete Maxwell's theory now in the relativistic thing. But because you can write it in terms of the Greek indices, the objects are actually tensors, and they transform nicely under the Lorentz transformation. And so this actually demonstrates that the Maxwell's theory is relativistic theory. Are there any questions? All right. Let me stop here and see you in the afternoon.